All right, for tomorrow we'll have the test over our sequences and series. We've mostly looked at series, but we may have a question or two dealing with just the sequence, so don't forget about that. But with this, again with the test, I will allow you one sheet of notes. And I'll talk here in a little bit of suggestion as to what you put on those notes. Make sure you have some of the details down and stuff. But in this test, there are 13 questions. Now, in this test, I do something that you've not seen me do before. I will allow you to mark out, omit one. You need to mark it out so I know that you're wanting to omit it. If you want to omit one, you can do all 13 problems and I'll grade it out of 13, but I think probably you'll find one that you're not sure of, so you can mark that out. I have had students that want me to grade all of them, which that's fine, I will. It's not going to be extra credit, but it would be instead of out of 12 questions, out of 60 points, you'd be out of 65 points. So sometimes that's a good thing, sometimes most of the time it's pretty obvious which one you're going to mark out anyway. But that is kind of one new, different thing that on this test I do allow you for that. So, okay, let's take a look at each section. We started out with sequences, and main thing there, notation, terminology, and then how we kind of took that the next step to the series and the summation notation and stuff. But sequence, something as simple as this. I may have you write out several terms of a sequence. Not sure how many I'll ask you for. Now, this would be, well, if n is 1, we'd have 1 over 1, or 1. I hope you can do that without a calculator. Then comma 1/2, comma 1/3, and so on. So sequence, each term is separated by a comma. Then in the next part, we got into series where you're adding all the terms together. But remember, this is sequence. We just list out the terms. Okay. Now, along with the sequence, a lot of the problems were find the limit of the sequence. So probably be a problem or two like that. Now again, this is the limit of the sequence, not whether the series converges or diverges and what it would converge to, but this is just talking sequences. Now we did mention if it's limited, it goes out to infinity, then that sequence diverges or sequence converges. Okay, and the limit value would be what it converges to. But that's, again, the sequence, not the sum, not the series. Okay? So, kind of laid the groundwork for working with the series. And then the next part we did define series and notation of series, infinite series, and then we started looking at specific types of series. But technically, the series part, what we've looked at so far is essentially when does a series converge, when does it diverge, or does it, I guess, not when does it, but does it converge, does it diverge? So from there we looked at lots and lots of different tests to see whether it converges or diverges. So some of the series, if they converged, we could find exactly what it converged to. And there might be some problems like that. What does the series converge to? And the two types of series we looked at there were geometric series and what other type? Do you remember? Okay, the telescoping series. So those two series, not just a rule, do they converge, do they diverge, but if they converge, what do they converge to? Okay. And both of these, you may have to kind of adjust the form that were originally given, especially the telescoping, something like that. Well, to adjust the form to get it into the telescoping, you would have to do what? Okay, partial fractions. So make sure you get it in that partial fractions. And then from there, see what it converges to. Telescoping sums pretty much always converge. It's just a matter of find what it converges to is the tricky part. And the most work on that are the partial fractions. Okay. So geometric, telescoping, kind of the first two types of series we looked at, and whether it converges or diverges. Questions so far on that? The next particular test we looked at were the nth term tests for divergence. And this test really didn't show whether it either diverged or converged. All we could say is from the test it diverges, or we can't use this test. So the nth term test, you remember what it was? If the limit of the, what I like to call the sequence term, the a sub n, okay, if that limit did not equal 0, if it equaled 1 or 3/2 or 2/5, something like that, then the series diverges. If it equaled 0, well, we don't know. Some of them still went ahead and diverged, some of them converged. So equaling 0, we've got to throw that test out and try something else. We have plenty of other tests to use, but that's probably one of the easier, quicker ones to use. So that might be one of the first ones you want to look at. But we have that one. Then we looked at the integral test. And that was ended up kind of involved. long process. Sometimes that was the best test to use, but a lot of times, a lot of these series, we could find an easier test than the integral test. Not always. Sometimes you have to use it, but the integral test would be a decent one to use in some cases. You just have to go through all the integration, and if it's an easy integration, then it's not too bad. But if the integral from 1 to infinity, if our improper integral diverges, then the series diverges. If the improper integral converges, then the series converges. Pretty straightforward as far as the test goes. It just can take a little bit calculating the integral. Now, to me, the best use of the integral test is proving what's called the p-series test. And the p-series test is in the form 1 over n to the p, and it's basically just a comparison of what p is. If p, for this series to converge, what does p have to be? Okay, greater than 1. And for if it diverges if p would be less than or equal to 1. And again, that is the test we can use, but again, it's proven from the integral test. I'm not going to have you prove it, but you can just say by the p-series test, p equals 2, which is greater than 1 if you have 1 over n squared. P equals 2, greater than 1, so it converges. Or if we have 1 over square root of n, well, p is 1/2 less than 1, so the series diverges. Okay. So, let's see. That's 5 tests already. Geometric, telescoping, nth term test for divergence, integral test, and p-series test. Okay. Next, we looked at a couple of comparison tests. Direct comparison, yeah. And that one, we had to, if we had a really ugly series, and especially if we had something like that where, well, sine of n makes life a lot more difficult. I wouldn't want to try to do any of these other tests on this particular type, but sine, cosine, I mean, some of those where the value could bounce around between positive and negative and not even alternating, but 2 negatives and then a positive and then a negative and 2 positives. That doesn't fit any of the conditions. So, but direct comparison, what would be a good comparison for this one? I would say 1 over n squared. That's a very easy one. And then what I want you to do is make sure you state the tests and why they diverge or converge. This converges by the p-series, and then compare, well, this less than or equal to 1 over n squared? Well, there you'd have to do some some comparisons and so forth. We know sine of n is less than or equal to 1, and then multiply both sides by 1 over n squared, and that shows sine of n over n squared is less than or equal to 1 over n squared. So by the direct comparison test, this series would converge. So direct comparison, there's a few steps on it too, but it can be fairly straightforward, especially dealing with the sine and cosine. Next comparison test, the limit comparison. And although this one looks a little more complicated, as you get into it and as you work through it, it may actually be the easier of the two comparisons. I'm going to take the limit of the ratio a sub n over b sub n. A sub n is the one we're given, b sub n is the one we choose. So again, if it's that sine n over n squared, well, in this rare case, this one would not be a very good limit comparison. What happens when we do this? Well, we get to limit of sine of n. Well, sine of n just kind of bounces between -1 and 1, so we really can't do a whole lot. There's a restriction on using the limit comparison, which would not allow us to use this in this particular case. The restriction, one of the restrictions is if a sub n is positive and b sub n is positive. All of the terms for both series must be positive. So that's why this one, sine of n, is not always going to be positive. So we couldn't use the limit comparison on this one. Okay. But a lot of the series, the limit comparison would actually be a better one to look at than the direct comparison. So I'll just cancel that out. But if we do use this and find out the limit exists, is positive and finite, meaning does not go off to infinity, then the original series converges if the series we chose converges, and vice versa. If we choose a series that diverges, then the original one diverges. So it's basically figure this out, and then whatever we chose, the series we're looking at does the same thing. Okay. Then we got to the alternating series test, and again the -1 to the n, or n plus 1, the sign will change, positive, negative, and so forth. If that's the case, then we can kind of just isolate on a sub n, see what happens there, and with the correct details. The main thing here is if the limit equals 0, then the series converges. Now, we got into a couple special cases, which on the test I will ask you about as well. Absolute convergence or conditional convergence. And that deals with, well, absolute convergence says if you can take the absolute value of the series term and show that that series converges, then the alternating series will also converge. No question on that. If the series with all positive terms converge, then the series with some negative terms will definitely converge. The conditional convergence is maybe the alternating series converges, conditional, probably the easiest one there. That one will converge by the alternating series. But absolute value of that series of 1 over n diverges by, well, pick a test. P series would be the most straightforward. So the series we were given with both positive and negative values converges, but take the absolute value of that, the other one diverges. This would be an example of conditional convergence. So there will be probably a couple problems on absolute convergence or conditional convergence. Okay. And then we finished out the sections with probably two of the easier ones to the ratio test and the root test. And really the results of both of these give us the same thing. Do the appropriate operation, either a sub n over, or a sub n plus 1 over a sub n for the ratio test, or take the nth root of a sub n and simplify the limits. If the limit is, what's the condition? You remember? Less than 1. Okay. Then it converges. If the limit is greater than 1, then it diverges. If it's equal to 1, then yeah, we have to try something else because it doesn't tell us anything. But ratio test, root test, for particular types of series, those are probably the easiest ones. Okay, so the way I'm going to word these problems, or at least most of these, if it's convergence and divergence, it is, well, I should have wrote down the exact way, but something about find whether the series converges or diverges. State the test used. And show the conditions are met. So the conditions for the test. You can't just say, well, this series converges. You got a 50-50 shot, not even looking at it. You got to be a little more specific than that. So But state the test you're using and then show the conditions why it converges or why it diverges. Now, the bulk of the problems will be, here's a series, does it converge or diverge, and all this. So what you need to work on, probably the biggest part of this, is recognizing what test you can use. And more importantly, what's the easiest test you can use? Because some series you might be able to use 4 or 5 different tests on. We want to find the easier one, the easiest one, if at all possible. So my suggestion would be list out in order of priority the tests that you can use. Which one do you want to use? Which one's the easiest one for you? Then which one's the next one, and the next one, and on down. And it will be different for all of you, but it will probably be similar. Integral test will probably be one of my lowest ones, although once in a while it may be the best or only one you can use. But the comparison tests, to me, they're a little more difficult than these other more straightforward. But again, it's all a matter of preference for you. You've got to figure out what's the easiest for you, what's the most difficult. But I would definitely write down the list of tests in that priority. Geometric, telescoping, P-series. Now, all 3 of those are very, very specific types, and all 3 of those are fairly easy to work through, so I wouldn't necessarily go with number 1 on geometric, but right up there, I would have the nth term test. Let's see, of these others, well, alternating series is pretty straightforward, but that, again, is a very specific. If you got your -1 to the n or n plus 1, something like that. The ratio test, root test, I'd almost go root test next for me. But again, that's going to be a very, very specific one. If everything's raised to the n power, yeah, use that root test. Ratio test is very useful for a lot of different reasons, but it can get a little more involved as you go through the ratio and simplify and stuff. Yeah, and then probably limit compare, direct compare, integral test. Let's see, is that all of them? You better make sure you have all of them, but I think that's all of them, but definitely that would be probably pretty close to my order, my priorities. You may have some rearranged a little bit, but it's all going to be up to you. So basically, here's a bunch of series. Does it converge? Does it diverge? What test are you using, and why does that test work? But those will be the bulk of the problems. Now, some of the individual problems, we kind of talked earlier, the sequences, limit of sequences. If a series converges, what does it converge to? Again, those would be limited to these 2 types. And there's one more type of problem that deals with your geometric, and that's your repeated decimal. Now, we did a few of these on the homework, but what fraction does this come from? Okay, and what you have to do there, turn this into a geometric series and then use the a over 1 minus r to figure out the fraction. So we did a few of those, but let's see, it'd be 10,000. And so on. And then from there, figure out A, figure out R, and do your A over 1 minus R. So that's a little different than, here's a series, does it converge or diverge? But that's one of the really nice uses for the geometric series. Okay. And then, well, there were some applications in there that you basically ran into this, but I'm not going to throw any of those applications at you. But some good real-world applications in that homework section. But let's see, I think that's pretty much it. So 13 problems, and again, I will allow you to omit one. If you want to omit one, make sure you mark it out. If you don't mark any out, I will grade all of them, and you'll have it out of 65 points instead out of 60. So make sure you mark it. I'm sure you'll figure out pretty easily. And you only get to mark one out. I will be checking that. So, but any questions?